Hello friends, welcome to EC Academy. In this video, let us talk about silicon on insulator CMOS fabrication process, which is also known as SOI CMOS fabrication process. Before we start the step-by-step fabrication process, let us understand what is silicon on insulator means. Normally, when we make a CMOS chip, we make them big and solid blocks of silicon. This is known as bulk silicon. But these bulk silicon are having a lot of problems. These bulk silicon will have parasitic capacitance and spatial inefficiency that will lead to crosstalk and leakage current. So, scientists come up with a smart idea to solve this problem. They used a glass or an insulator below the silicon. So, if we use glass, that will act as an insulator. It will completely isolate the devices. It reduces parasitic capacitance, improves the efficiency, it will provide the electrical isolation, and it will have an organized pathway for current flow. This is how the silicon on insulator looks like. Since we are using an insulating substrate, it will provide isolation between the devices. Hence, there will be no body effect and there will be no field intervention, and it will reduce the latch up also. Now let us understand how we actually build this by understanding step-by-step fabrication process. Step 1 is a substrate preparation. In this step, we'll start with our base foundation. Here, we take an insulating material which is a sapphire. Over this sapphire base, we grow a thin layer of lightly doped N-type silicon. The thickness is just about 7 to 8 micrometer. Step 2 is island formation. Now, we don't want silicon everywhere on the chip. So, we use a chemical processing called as anisotropic etching to cut the extra silicon. This will leave behind small isolated blocks of silicon on the top of sapphire. We call these blocks as islands. In the third step, we'll perform doping. Now, we need to change the electrical properties of some of these islands. So, we cover the area we don't want to dope and we add a p-type dopant like boron in a specific island carefully. So once we add boron implant, the p island will be formed, and these p islands are used to make n-channel devices. This is about doping for p island. Step 4 is doping for n island. Similarly, how we used mask on n island, after formation of p island, we'll use mask on p island and we'll dope the n-type dopant, which is phosphorus. Since phosphorus is n-type, that will form the n island. So these n islands are used to make the p-channel devices. So p islands are used for n-channel devices and n islands are used for p-channel devices. Step 5 is gate oxide formation. In this step, we need to put a very thin protective layer over this silicon, which is a gate oxide. This is done using thermal oxidation. We grow this thin layer of gate oxide about 500 to 600 Armstrong thick. This layer is formed above the structure. Step 6 is polysilicon deposition. In this step, we deposit a material which is a polysilicon over the gate oxide. We dope this polysilicon with phosphorus to make this a better conductor. So, once the polysilicon gate is doped, it will have very less resistivity and it is a better conductor. Then this polysilicon is cut in a shape so that we can form this as a gate for our transistor. Step number 7 and 8 is a source and drain formation. You need to remember that every transistor need a source where current will start and a drain where current will go. For a N-channel device that is sitting on a P island, we implant the N-type dopant like phosphorus into the source and drain region by using mask on the other regions of the transistor where the implant is not needed. Similarly, we'll put a mask on P island. Then we implant P-type dopant like boron that will form the drain and source region inside N island. During this process, the polysilicon gate will act as a wall which blocks the dopant going into the gate region. So, dopant will be formed only where the gate region is not present, so that source and drain with N plus and P plus material is formed. Step number 9 is insulator deposition and metallization. Now, our device is ready, but we need to wire them together. First, we cover everything with a phosphorus glass or silicon dioxide insulator on it. Then, we cut open the small holes and then we'll pour aluminum that will act as electrical wires. These electrical wires will connect everything inside the chip. The last step is passivation. After insulator deposition and metallization, we put one layer of phosphorus glass over entire chip to protect it from dust and damage. This process is known as passivation. So why do we use silicon on insulator? Let us understand the advantages. The first advantage is that it is faster and better. Because of the insulating sapphire base, there is a lower parasitic capacitance, which means the circuit will run faster. The second advantage is there is no latch up. So this device are totally isolated, so they don't interfere with each other and latch up will not occur. The third advantage is radiation tolerance. These chips survive very well in high radiation areas. That is why they are used in aerospace and military applications. But there are few challenges. The first challenge is that they are very expensive. The second challenge is that the processing is very much complex. So there are two major challenges. First one is that they are very expensive and the processing is very much complex. Now let us quickly revise what we have learned today. We start with a sapphire base and put silicon on it. We cut the silicon into separate islands. We dope them to make P islands for N devices and N island for P devices. We add gate oxide and polysilicon gate. We create the source and drain using dopant. And finally, we wire them with aluminum and protect them with a final glass layer. This is about silicon on insulator fabrication process. Hope you have understood the topic. Thank you.